Good morning, class. Today we will discuss section 8.3, which talks about estimating population means, mu, when sigma is unknown. And remember that sigma is our population standard deviation. Now, a fact, when the population standard deviation sigma is unknown, the sample taken is a simple random sample, and either the sample size is at least 30 or the population distribution is approximately normal. The margin of error of a confidence interval for a population mean mu is given by the following formula. And again, this is one of our formulas listed on our exam 4 formula sheet. So notice it looks very similar to section 8.1, except our z value has now turned into a t value. And since sigma is not known, we're going to use a point estimate. A good point estimate for sigma is s, which is our sample standard deviation. We saw in section 8.1 that if we are given a confidence level C, then our alpha, 1 minus C, represents the remaining area in both tails of our Z distribution. We will use this same idea along with the student's T distribution, which is table C. That is, T alpha over 2 is the critical value for which the area under the T distribution with n minus 1 degrees of freedom to the right of T alpha over 2 is equal to alpha over 2. Let's look at an example. Dental researchers want to estimate the mean leakage measured in nanometers of a new filling material for cavities using a simple random sample of 10 trials. Assuming that the population distribution is approximately normal and the population standard deviation is unknown, find the margin of error for a 95% confidence interval for the population mean given that the sample standard deviation is 15.5 nanometers. Now, notice that in this problem, our population standard deviation is unknown. Now, this may confuse some of you because we read it as assuming the population distribution is approximately normal. Sometimes you see this word assuming and you go, oh, that's sigma. This isn't sigma. This is just saying the population distribution is normal so that we can use the T distribution because our sample size is very small. If our sample size wasn't so small, we wouldn't need to make this statement. Okay, so that's all that's telling us, is that here, because our population standard deviation is unknown and our population distribution is normal, we can use our T distribution, okay? All right, so we know from the problem, our sample size is 10, that's n. Our confidence level was 95%, and our sample standard deviation, which is denoted by S, is 15.5. Since the problem states that the population distribution is approximately normal and the population standard deviation is unknown, we are able to use the T distribution to calculate the margin of error E. First, we need to find our critical T value. So first, we calculate n minus 1. So again, on your exam 4 formula sheet, you'll see that right next to this formula, it will say df equals n minus 1. So that reminds us that the degrees of freedom is 1 less than the sample size. So our sample size was 10, 1 less gives us 9. So that's going to be our first column we look at. Degrees of freedom is 9. Now we need to find our alpha. Alpha is going to represent the area left over in the tails. So alpha is 1 minus our confidence. And this we saw in section 8.1. So we get 0.05. So therefore, we can do it two ways. So we can either look at half of this, and this would be an area in one tail, or we can use this by itself, and this would be an area in two tail, Either way, we see that our critical t-value is 2.262. Now, pause the video and make sure you see this value. You get this value on your own, because this is a very important part of this problem. So note that since alpha represents the area left over in the two tails, we could look across for an area in two tails. So again, one method is to divide it and look at area in one tail. Another method is to just leave it as is, which is probably what I would do. Why do more work when you don't have to? And just look up this value in the area in two tails. So now we're able to calculate our error. So our error is our t-value times s over the square root of n. Plugging all of our values in, we get 11.087262. Let's put it all together and look at an example. So a student records the repair costs for 20 randomly selected computers from a local repair shop where he works. A sample mean of $216.53 and a standard deviation of $15.86 are computed. Assume the population's distribution is approximately normal. Determine the 98% confidence interval for the mean repair costs for all computers repaired at the local shop. Okay, so pause this and try to pull out all of the numeric values and correctly label them. Okay, now after doing so, check your work. So notice that we have 20 randomly selected computers. This is our n, right? Our sample size. And we're told that a sample mean, this is our x bar is $216.53. Now here, notice they just say standard deviation. So the question is, does this represent S or does this represent sigma, like we saw in section 8.1? But notice it's saying that it's computed, right? Both of these are computed values. Computed from where? We're assuming that we're computing them from the sample. So this is actually our sample standard deviation. Okay? They're not going to explicitly say sample standard deviation is this. You have to kind of interpret this through the sentence structure, right? Since this standard deviation is being computed, and it's assumed that it's being computed from these 20 randomly selected computers, it represents our value S. And then finally, here's our confidence level, 0.98. Okay, so recap, n equals 20, x bar is 216.53, s is 15.86, and c is 0.98. Now we need to find our t-value. So we first use our confidence level to find our critical t-value. So notice, and a side note, the degrees of freedom is always one less than the sample size. So our degrees of freedom is 19, and we need an area in one tail or two tails. So I need an alpha, right? Remember, alpha is the leftover area in the tails. So my alpha is 1 minus c, it's the complement, so I get 0.02. I'm not going to divide this by 2, I'm just going to use this value in my area in two tails, in table C. So looking across the row for 19 degrees of freedom, and down the column for an area in two tails of 0.02, we get a critical t-value of 2.539. And again, pause the video, look at your table C, and be sure that you get this value as well. This is a very important part of this problem. We can now compute our margin of error. So our margin of error, plugging in our t, our s, and our n, we get 9.004319. Now, we wanted to find not just the error, but we wanted to find the 98% confidence interval. So remember, how do we do that? From section 8.1, we take a starting point and we subtract our error and we add our error. What's our starting point? It's our x bar. So I'm going to take x bar, which was given as 216.53, And to find my left endpoint, or my lower endpoint of the interval, I'm going to subtract my error, getting approximately 207.53. And my upper endpoint, I'm going to add my error, getting approximately 225.53. So this gives us the following interval. Now, using our graphing calculator or smartphone app, again, what we're going to do is click Stat, and we're going to highlight our test here, and instead of selecting our Z interval, this is what we did in 8.1, we're going to click on our T interval, okay? And input the given values from the problem. So again, the problem gives us single numeric values, single numeric descriptors. These are our statistics. If it gave us a bunch of raw data, we would click on the data feature and input our data into column L1 using the edit feature in our calculator. In the problem, we're given that our mean was 216.53. Our standard deviation, S, was 15.86. Our sample size, N, was 20. And our confidence level was 0.98. And now what I'm going to do is hit enter. And I get my confidence interval 207.5 approximately to 225.5. Now remember, to estimate our margin of error, we can subtract the sample mean from the upper endpoint. Right, so I'm going to take my upper endpoint, 225.536032, and I'm going to subtract my sample mean, 216.53, and I get approximately 9.006032. And we can compare these, so let's go back. Close, very similar answer here. We got, when we calculated it by hand, we got 9.004 approximately. And when we did it with our calculator, we got 9.006, very close. And our interval was 207.5 to 225.5. And notice we actually got a very similar interval here, 207.5 to 225.5. So whichever way you feel most comfortable solving these problems, whether it's using your calculator or using the tables, the appropriate tables, and doing it by hand, that's okay. Just remember that on the quizzes and the exam, I will ask you to calculate the error. So even if you're using your calculator, remember that this is the trick to find our error.